So this week, we're going to focus on two types of functions. First ones we're going to look at are called exponential. And the second ones we're going to look at are called logarithms. We might have done a little bit with logarithms in Algebra 2, maybe not, it depends. But we'll take a look at it. So first thing, I just want to look at these two expressions. One of them says x squared, and the other one says 2 to the x. In each one of them, there's something called a base, and then there's something called an exponent. Let's look at the one that I just circled first. Anybody tell me, what's the base for the one that's circled in red? Yep. Go ahead. X. Yep. Base is x. And Sam, what's the exponent for the one that's circled in red? 2. Exponent, bless you, is 2. When you put the base as a letter and you put the exponent as a number, this type of thing right here, that's called a polynomial. Okay, that's a polynomial. The one on the left that I put a box around, that is not an exponential. Polynomials are things like parabolas. When you draw a parabola, that's a polynomial. That is an exponential. One thing that you look for that makes something exponential is the exponent is a letter. Okay, the exponent is a letter. That's part of what makes something an exponential. When the base is a letter, that's more of a polynomial. That's not an exponential. So, any question on the difference between those two? I know they're similar, but the base and the exponent are flipped. That says base, in case you couldn't see it. Now, I said that having a letter in the exponent, that's one thing you look for. There's one other thing that has to happen to make something an exponential. And I'll tell you what that is in a minute. But first, that's describing the kinds of things that we've studied before. When you have a variable in the base, and the exponent is an integer that's not negative, that's a polynomial. Okay, when I say it has to be an integer, can somebody remind me, what does an integer mean again? Yeah. Yeah, it's a number that doesn't have a decimal. Specifically, we're looking for a number that's not negative. So it could be a 1, 2, 3, 4, 5, any number like that. So here's another example of a polynomial. You look at each part and say, okay, is the variable in the base? Yep, x is in the base. Yep, x is in the base. And the next thing is, you look at the exponent and say, okay, is the exponent an integer, which means it's not a decimal, and is it not negative? Yeah, 3 is not negative, and that doesn't have a decimal. 2 is not negative, and that doesn't have a decimal either. So that fits the definition of a polynomial. That's the thing on the left. Now, on the right, I told you there's two things you have to look for something to be exponential. First is that there is a variable in the exponent. That's one. But the other thing is the base. The base has to be a positive number, any number. This could be a fraction or a decimal, but it has to be positive, and it cannot equal 1. Can't equal 1. Why do you think this would not be a polynomial? 1 raised to the x. Yeah? It would always be 1, right? 1 times itself 5 times. 1 times 1 times 1 times 1 is still 1. So if the base is 1, you're basically graphing something that's a straight line. That's not exponential. The base either has to be bigger than 1, or it could be between 0 and 1, but it cannot be a negative. And you'll see when we draw some of these graphs, they're gonna curve. Okay? These kind of graphs, they stay flat for a little bit, and then all of a sudden they start to curve up very fast. Or you could have the mirror image of that. It can curve down really fast, and then look like it starts to flatten out. Never really flattens out. It just gets flatter and flatter and flatter as you go. But it does still keep dropping a little bit. One of these is called exponential growth, and the other one is called exponential, anyone know the other name? Opposite of growth? Yeah? Decay. Very good. So one of them is growth, one of them is decay. Whether you have growth or decay, it all depends on what the base is. You can tell just by looking at that one number. Let's graph an example. So I'm going to pick a base. I'm going to let my base be 2. So I'm going to graph y equals 2 to the x. To type in an exponential, it's pretty straightforward. You just need to use the caret above the division sign. That'll give you your exponent. Put your variable in. And when you type it in, it should look just like that. Okay, let's graph. We'll do zoom 6. You're going to see this one's flat on the left, and then all of a sudden, it starts to curve. Okay, anyone have an idea how far left that graph is going to go?
Forever.
Yep, it's just going to keep going. It's going to keep going to the left forever. And when it goes to the left forever, what do we say it's going towards? Negative infinity. And how about to the right? What is it? Regular infinity. Yeah, it's going to keep going to the right. It does go up faster than it goes to the right, but it's slowly, if you keep drawing it, it's going to keep making its way to the right. So every exponential function has a domain of all real numbers. And that's not just true if I graph 2 to the x. I could do 3 to the x, 4 to the x, 10 to the x, 100 to the x. I could graph any value I wanted for a that's a positive number, not equal to 1. That's what we just said on the other page. 0.5, you could do that one. That one would be a little different because it's a decimal, so that wouldn't be more. It'll be more of a decay than a growth because it's a decimal. So the domain for exponential functions is always all real numbers. You can never change that. Well, if we look at the range, that's how high and low it goes. I can see that it goes up further. Okay, if I look at the right side, it just keeps curving up. But does it look like this graph goes down further? No, what does it look like it's leveling off at? Yeah, it is. It's leveling off at 0. It's never going below 0 in this particular graph. The range is something you can change. Like if you take this graph and shift it down 1, well, now the range would be -1 to infinity. Right? So we can change the range, but we cannot change the domain. Ever, no matter what you do. Any questions on why the domain is all real numbers? Okay, so those are all examples of exponential functions. Look at each one of them and see if it meets the definition. Does it have a base that's positive and not 1? 10, 4, 3.14, yep. And does it have a variable as the exponent? X, V, and X. So yes. So those are examples of exponential functions. These are not. Why isn't this first one an exponential function? What's wrong with it? Yeah.
Just because the exponent's not a variable.
Yeah, the exponent is supposed to be a variable, so that's the problem with the first one. That's also the problem with the second one. And the third one, well, that doesn't fit the pattern that it's supposed to look like. It's supposed to look like this. Y equals, at least in the simplest form, it's supposed to have a base raised to a power. That's not what this one looks like. So none of those are exponential expressions, functions. Any questions why these bottom ones are not exponential functions? The first two are polynomials. The last one, it doesn't really fit into a category. Let's look at the difference between these two. So we're going to graph 2 to the x. We've already done it. And then let's graph 3 to the x. Think about each one of them. If you raise 2 to a power, or you raise 3 to a power, which one gets bigger faster? The 3 to the x. Like even if you just cube it, 2 cubed is 8, 3 cubed is 27. So 3 to the x gets a lot bigger, a lot faster. So if you graph each one of them, what you'll see with 3 to the x is it's going to curve up sooner. It's going to start to increase faster. And there's a picture showing the red line. Once it gets past the y-axis, it starts to take off quicker than the blue one. And if you graphed 4 to the x or 5 to the x, it would curve up even faster. Okay, so what's going to happen sometimes when we look at exponential graphs is they're going to have negatives in the exponent. When there's a negative in the exponent, that kind of complicates it. We'd rather not have it. It's simpler if we don't. So I'm going to show you how we get rid of it. Does anyone remember what something like that means? I know 5 to the second means this. But what happens when you have a negative in front of the 2? You're going to end up getting a fraction, right? So this still means to do 5 times 5, but it means to do it in the bottom of a fraction. So a negative exponent means that it's in the bottom. So it's the difference between 25 and 1 over 25. So, let's pretend like we didn't have a number, we just have a to the negative 1. Okay, anyone tell me what does a to the negative 1 mean? If we don't want to write it with a negative exponent. Yeah.
1 over a is the first power.
Right. Just means 1 over a to the first power. That's a to the negative 1. So let's look at what happens if we had a to the negative x. And I want to see if there's something I could do. It's going to use this rule to get rid of that negative right there. So if I write a to the negative x, when you write a variable, there's always a number that's understood to be there. What number is in front of the x in that case, even though it's not written?
1.
Right, so there's a 1 right between the negative and the x. So what that really means is this. And there's a rule from algebra. I'm going to give you a hint. If you had this, does anyone know what the answer to that would be? 2 to the third to the fourth? Something you do with the 3 and the 4 here. Yep.
Multiply and you 2 to the 12.
Yes, you multiply them. So what I'm getting at here is the only way that you would end up multiplying two numbers together in an exponent is if originally you had a power to a power. So that's how I want to think of this. Think of a to the negative 1 times x as a power to a power. Because a power to a power means to multiply those two things together. And what did we just say a to the negative 1 is? We said that was 1 over a. So there's a way that you can get rid of a negative in front of the x. So what, without going through all these steps every time, what basically happened to go from here right to that? Anyone tell me what do you do? Yeah.
Putting the base on the bottom and putting the exponent on the outside of parentheses.
Yeah.
Making a fraction.
So if you had this, can you tell me what that would be without a negative in front of the x?
Parentheses 1 over 4 and parentheses and then x.
So 1 over 4 to the x. So this negative basically tells you to take your base and flip it and leave the x on the outside, but now it becomes positive. So that's a trick we can use anytime we have a negative in the exponent and we don't want it. We'll just flip the base and that takes care of the negative. And I think it's the same thing I had right here. Yeah, so you don't have to write that. You just did. Okay. Any question on that rule? All right. Did that, did that. All right, so let's graph these two, and let's just look at them. But before I graph it, I have 2 to the negative x. We just talked about how to get rid of that negative. I want to try it again right here. So, Grady, can you tell me how I could rewrite the bottom without that negative?
You could have it 1/2 of x.
So 1/2, and then what?
Have the x be the exponent.
And have x be the exponent. There we go. Now the reason we want to do that is because when I look at this quickly, I see that this base is bigger than 1, and I see that that base is smaller than 1. That tells me something. Well, let's graph it and see what it tells us. Okay, so I'm going to leave 2 to the x on y1. And I'm going to put in 0.5 instead of 1/2 just because I don't want to have to do the parentheses. So 0.5 is the same thing. So type that in. And then hit zoom 6. Okay, so the first one you're looking at is 2 to the x. And then we're going to look at 2 to the negative x, or 0.5 to the x, same thing. Let's make that so we can see it a little better. Yeah. Does anybody see a connection between the one in blue and the one in red? They cross at the point 0, 1. Yep. And how about in terms of, like, if you wanted to turn one into the other? Does anyone see the transformation? They're what? They're mirror reflections over the y-axis, right? They're flipped over the y-axis. So they have mirror images of each other. The one in blue is called exponential growth, and the one in red is called exponential decay. So let's look at those two graphs and see if we can determine the domain and the range of each one. Well, we've already done the one in blue earlier. What was the domain of the one in blue? Well, Curtis?
The domain.
Yeah.
It's positive.
Okay, so goes the highest is positive infinity. How about the lowest for the domain?
The lowest is 0.
That would be for the range. That'd be for the range. You want to remember, what did we say the domain was? For all exponentials, this can never be changed. Yeah? Yeah, the graph in blue will go left and right forever. And Austin, how about the graph in red? What's the domain for my graph in red? So I need an interval from this to this. What did we say the relationship was between the red and the blue graph again?
I don't know.
Did someone remind him what's the relationship between the red and the blue? Yep.
They're mirrored of the y-axis.
They're just mirror images. And the blue one goes to the left and the right forever. So what's going to happen with the red one?
It's gonna go.
You want to help him out? What's going to happen there? Oh, Cameron?
Is it also going to go left and right forever?
Right. If the blue one went left and right forever and you flip it, well, it's still going to go left and right forever after you flip it. So the domain for both of these is all real numbers. So negative infinity to infinity, negative infinity to infinity. Now, how about the range? What's the range of the graph in blue? That's up and down. Yeah? The blue one is 0 to infinity. It starts at 0, never touches it, goes up forever. So the blue one is, just to color code it for you, that's the blue one. That's the red one. What about the red one? What's the range on that?
Would this still be 0 to infinity?
It's still 0 to infinity. So even though these are mirror images of each other, they have the exact same domain and range. Now, we looked at this specifically for the graph of 2 to the x, but it would be true for the graph of 3 to the x as well. The only thing different is the curve would be a little steeper. So the key difference between f of x and g of x, let's just go back for 1 second. This was f of x. Look at the base. There's g of x. The key difference is what the base is. If your base is greater than 1, that's going to give you an exponential growth graph. 2 to the x, 3 to the x, 5 to the x, 12.7 to the x. Any number bigger than 1 is going to give you exponential growth. Any number between 0 and 1, 0.5, 0.2, 1/3, that's not going to be exponential growth. That graph is going to decrease. Does anybody remember what I called it? It was the red one. That was the mirror image. That's called decay. Growth is about something increasing. Decay is about something decreasing. And what about if the base was exactly 1? What happens there? It just stays 1 all the time. That's not something we're talking about. That's not exponential growth or decay. The base cannot be the number 1. We already said it. Right. So any questions on the difference between when you get a growth or a decay graph? Okay, so I'm going to ask you guys, I'm going to call on someone and see if you can tell me when it's growth versus decay. All right, so Kiana, would that be a exponential growth or exponential decay? Which one? That's growth, because that has a base bigger than 1. How about 2/3 to the x? Growth or decay?
Decay.
It's decay, right? The base is less than 1. 2/3 is like 0.6 repeating. This is decay. How about y equals that one? 3/2 x. Yeah?
Growth.
That's growth. You may say, well, wait, you said fractions are decay. No, I said if it's less than 1, it's decay. That's 1.5. So 3 divided by 2 is a base of 1.5. So that's growth. Okay, any questions on that? All right. So let's look at transformations. Transformations with exponentials work exactly the same as every transformation we've studied. There's no difference. So let me write out like the template that'll help you. And let's identify where's the horizontal shift, where's the vertical shift, where's the horizontal stretch, and where's the vertical stretch. All right, so we would have base. We could multiply by a number in front. Have a power there. Times x. We could have a plus or minus. We could have a plus or minus at the end. I'll put letters in those boxes as we go, so you know which one is first, second, third, and fourth. Okay. So if you had a number that was added or subtracted in the exponent, that is the first thing you would do. And does anybody remember when you add or subtract, is adding and subtracting a stretch? Or is adding and subtracting a shift? What does adding and subtracting do? Yeah, that's a shift. We have two adding and subtractings. One is inside the exponent. The other one is on the end, outside the exponent. Does anybody remember what adding and subtracting inside does? Yeah? Yep. So A is a horizontal. You know what? I need more space. So what I'm going to do is I'm going to go like this. It's A, horizontal, shift. If A is positive, which way does positive move you? Left or right? Which way? Left. Yeah, positive is opposite of what you would think. Positive is left, negative is right. Let's look at this one. So this is D. I know it's the last one, but I'm going to jump to it now because it has something in common with the one we just did. This is adding or subtracting, but now it's on the end. It's outside the exponent. What does adding and subtracting do when you put it on the end?
It's the shift, right?
And what kind of shift is this one? This is a vertical. So this is your vertical shift. What if D was a positive number? Which way would that move it? Up or down? Up. This is what you would expect. Positive is up. Negative is down. Okay, so adding and subtracting is a shift. Now we're going to look at the two that are multiplying. B. B is multiplying, so it's not a shift, but it's still inside the exponent. This whole thing right here is an exponent. So what do you think B is going to do since it's multiplying, but it's up in the exponent? Is it going to be a horizontal or a vertical?
Vertical.
Well, was A vertical?
No.
No, because A is up in the exponent, and B is also up in the exponent. So B is also vertical. It's in the exponent, it's vertical. But what do you think B is going to do? About 1. So what kind of transformation is B going to do? It's not a shift. It's going to be a stretch. In what kind? Horizontal or vertical? You said vertical?
Yeah.
Okay. Anybody agree or disagree with that? Yeah.
I think it's a horizontal stretch.
It's horizontal. Remember, if it's in the exponent, it's horizontal. So in the exponent is horizontal. So horizontal stretch. And how about C? It's multiplying like B is, but this time it's outside the exponent. So look at the two things. Multiplying tells you one thing. Outside the exponent tells you something else. Yep. It's your vertical stretch. And we usually write like vertical stretch by a factor of, and then put the number. Now, one other thing that can happen with B and C is they could be negatives. What would happen if C was a negative number? Not only would it cause a vertical stretch, but it would also cause a, what kind of reflection? Over the x-axis, yes. If negative, reflect vertically. vertical reflection would look like this. That's a vertical reflection. How about if B was negative? What would that do? Yeah? That would reflect over the y-axis. And over the y-axis means horizontally. So horizontal, if negative, reflect horizontally. That would look something like this. Okay, so that's what each number does. Not every problem is going to have every number in it. And the base, well, the base doesn't really matter. They'll give you a base in the problem. That's just the base you're going to use. But you want to be focusing on the A, B, C, and D. All right, so let's try one. So this says, list the transformations to turn f of x into g of x. First, when you look at g of x, how many transformations are there? It's always good just to try to identify how many there are first. How about, Tony, can you tell me how many there are? 3. Yep, there are 3 transformations. And it just says to list them. Let's list them out. Tony, can you tell me what number are you looking at that tells you the first one? The 2, the plus 1, or the minus 5?
That's 1.
Yep, you're looking at the plus 1. So look at where the plus 1 is. Look at the chart we just made. And figure out which way a plus 1 is going to move the graph. Sam, can you tell me what the plus 1 is going to do?
Yeah, horizontal shift.
Yep, so it's going to be a shift left 1. If you want to say shift horizontally left 1, that's okay too. All right, so we took care of the plus 1. B, I don't have a B value in this problem. There's no number in front of x. So then we're going to go to the next one, which is C. Okay, what's the next number I look at there? The 2 or the negative 5? Right?
It'd be the 2.
Be the 2. Can you tell me what the 2 is going to
It'd be the vertical stretch by 2.
So vertical stretch. So first you got to tell me what type of stretch and then how much. A factor of 2. Okay, there's that one. So the last thing we're going to be looking at is the minus 5. Jackson, what's a minus 5 on the end going to do? Let's take a look. So what letter represents the minus 5?
D.
The D. And what's minus do?
Down.
Down. So that's going to shift it down 5. Okay. Any questions on those transformations based on that chart? Okay, so were there any reflections in this one? Ted? No, there were no reflections in this one. Not every problem is going to have a reflection. Okay, so we got, does anybody need to copy that chart still? That's kind of important. All right, so the last thing we're going to look at is formulas to figure out exponential growth and exponential decay. Like if I said to you the population of the city goes up 2% every year, it's starting at 50,000 people, tell me what it'll be 5 years from now. That's what the formula I'm about to give you will figure out. So it says, suppose a population, which I'm going to call P, that's the population, it's increasing at a rate of R. For this to be an exponential problem, the rate of increase has to be a percentage. If you said to me 100 new people move to the town every year, that's not exponential. Just adding 100 every year. Exponential has to be an increase by a percent. Alright, let's look at the, whoops, skip the formula. That's the formula for what we call exponential growth. There's not a lot to it. It's just P times 1 plus R to the T. I should have labeled T. T is time. P is an initial amount that you're starting with. R is a rate of increase, but it has to be as a decimal. So for example, if I said to you 12%, can someone tell me what is 12% as a decimal? 0.12. Okay, so we have to write that as a decimal. Now, we've talked about two kinds of exponential graphs. One of them is growth. What's the other one that I mentioned and we saw a couple pictures of? Yep. Decay. You only have to change one thing in that formula to make it decay. One thing. Does anybody have a guess what in that box would change to turn that from growth to decay? Yeah?
Plus to minus.
Yep, you change the plus to a minus. So I'm not going to relabel everything, but if you said like you had, I don't know, 200 acres of forest and it was decreasing at 3% every year, how much would you have 20 years from now? That's a decay problem because the amount of forest is going down by 3% every year. P is initial amount, R is a rate as a decimal, and T is still time. And we're going to solve these problems on the calculator. Show you how to do it. Does everybody have the two formulas? So this one is about a town that is starting with 50,000 people, and the population is going up 2.5% every year. So the first thing they want us to do is write an equation that represents that. And then the second part, they're probably going to say, use the equation to figure something out. So the question that they're basically asking is, when is the population going to double? That's another way of wording what they just said. When are you going to hit 100,000 people? Okay, so we'll write our equation first, and then I'll show you how to use the graph to figure it out. Okay, first step is to decide, is this an exponential growth or a decay problem? If we use the wrong formula, we're going to get the wrong answer. Is this problem about something growing or decaying? Growing. What word tells you that this is about growth? Right, it says the population is increasing. So can you remind me, what's my formula, Sky, for exponential growth?
P parentheses 1 plus R parentheses
1 plus R
the T exponent.
for the T as the exponent. And remember, that's going to be equal to, in this case, a population. So let's just say that that's an amount. A just stands for amount as a function of time. Okay. So let's start with the P. Grady, what's the P again in that formula?
The additional amount.
Initial amount. So let's go up. What's my initial population of this town?
Oh, were you asking?
Yeah,
Oh, sorry.
50,000. So my town has a population of 50,000. Times 1 plus R. So now I need my rate. Before we write the rate, what did I say about the rate? It has to be what?
Written as decimal.
It has to be written as a decimal. That's a percentage. So what's 2.5 as a decimal? Yep. 0.025. That's your rate. 0.025. And the only thing we have to do to simplify it, we're just going to add what's in the parentheses, and that will be our formula. So 50,000 times 1.025 to the T. Here's my formula. Now, there's two types of questions I can ask you about this. I can either say, 20 years have gone by, tell me what the population is now. If I said 20 years had gone by, where would you fill in the 20? On the left side? Or would you fill it in for the T? You fill it in for the T because the T is time. This question is not about 20 years or 30 years going by. It's asking you to figure out when you hit 100,000 people. So the number that they're giving you, 100,000, that's not a time. That's an amount of people. So where would 100,000 go? On the left? Or for the T? It's going to go on the left. It's going to replace A of T. So we have 100,000 on the left. 50,000 times 1.025 to the T. And we are going to use the calculator, but we can simplify this a little bit. If you can divide both sides by something to make those numbers smaller, it's going to allow us to not have to set as big of a window. Does anyone see something both sides are divisible by? Yep. We can't add or subtract. Divide. We can divide both sides by 50,000. But only do it if it goes into both sides. Like if you could divide by 10, you could do that. Find the biggest thing you could divide by. 50,000 divided by 50,000 is gone. What's 100,000 divided by 50,000? 2. So now, all we have is this. That question is basically saying, what do you raise 1.025 to and get an answer of 2? Well, we're going to learn how to solve it algebraically later on. But for now, let's graph. Ryan, where do you think I would put the 2?
In its own spot.
Yep, so we're going to put that in its own spot. And then we're going to put 1.025 to the T in its spot. A different spot. But I can't use T. What letter do I always have to use? I always have to use X. 1.025 to the X. So I'm going to be looking for where Y1 and Y2 are equal. Well, what does that mean if you're looking for where two pictures are equal to each other? Yeah?
They intersect.
Where they intersect. Zoom 6. If you hadn't divided both sides by 50,000 and you put 100,000 in Y1, you're going to have to set your window huge. That's why we did what we did. Okay. Can I see where they intersect? No. So what, Curtis, what do I have to do here? So I can see where they cross.
Zoom out.
Yeah, well, what would make sense for would make sense to zoom out to. So what did you say? Which one should we set bigger?
The X max.
Yeah, the x max. We really don't even need to look at negatives in the x min. That doesn't make sense. Time, x is time. We can't have negative time. So we might as well put that at 0. We can't have negative people in the town. So we don't really need to look at negatives for y either. Let's just set our x max. Let's try 40. Hit graph. So there's my line at 2. Hopefully we're going to see that curve. So you can start to see the population. It's kind of starting to take off a little bit. It's a very slow curve, but it does hit it. Okay. Now, what do I want to press now?
Zoom.
Well, we got a good window, so we don't want to change the zoom. We want to do something else. Yeah.
Calculate.
Second, calculate, and we want to do option 5. So we're going to hit enter 3 times. So how many years have to go by before the population of the town hits 100,000 people? Yeah, about 28. A little after 28 years. So t is about 28.07 years. Okay. Any question on that one? Yes. Yep, just sign up. Yes.
So I'm writing that as an answer. We need to make sure that like equal sign is about.
Yeah, I put about because it's not exactly 28.07. It's about. So that symbol means about. All right. Basically, we just did that in the last problem. Be careful about including negatives in your window because sometimes negatives don't make sense. Negative people? No. Negative, well, there are negative people, but we're not talking about that kind of negative people. So, people less than 0? No. Time less than 0? No. Doesn't make sense. All right. What I want to look at now is a special type of growth, and that's when something doubles. So we're going to look at something double over time. If something is double, a lot of people get confused with what that means as a percent. It doesn't mean 200%. Does anybody know what the growth rate is if something doubles? It's not 200. 200 would actually be triple. Yeah? 100%. Like if I said to you, you need to do 100% better, or you need to increase your score by 100%. Well, if you had a 30 and you increased it by 100%, that means you add another 30 to it. That's double. That's 60% increase. That's a 60 now. So that's a 100% increase. So think about our formula. If you plug in a growth rate of 100%, what number would end up inside that parenthesis after you change that growth rate to a decimal? Well, the growth rate would be a 1, and then what would be inside the whole thing that I circled? A what? A 2. So when you put a 2 inside there, that's an exponential growth formula specific for something double. And there is the general formula for something double. Pretty similar to the last one. One important thing about the exponent, though. Start with the initial amount times 2. But that exponent that I just put a box around, that has to be the number of doubling cycles. So for example, let's say something doubled every 8 hours. And 1 day had gone by. How many times would something double if it doubles every 8 hours after a period of 1 day? 3 times, right? 3 times. So this exponent, to represent something doubling 3 times, would need to be a 3. We wouldn't want to put in like 24 here, just because one day had gone by. If you put a 24 for that exponent, you're telling me that it's doubled 24 times. No. So this exponent is the number of doubling cycles. So you take your time and divide by the length of the time to double. So 24 hours in a day, divided by 8, it's going to double 3 times in one day. All right, so let's try this. Suppose we have 100 bacteria in a petri dish. What's the 100? That's like my what? That's the initial amount. And this one is doubling every 1 hour. So in this case, it is true. If 5 hours have gone by, it's doubled 5 times. 6 hours have gone by, it's doubled 6. But that's only because it's doubling every 1 unit. It's not like it's doubling every 8 units. Okay, so it says, when will we hit 350,000 bacteria? And I can do a quick estimate with my calculator. If you want to get a rough idea, take 100 times 2. So after 1 hour, I'll have 200. After 2 hours, I'll have 400, 800, 1,600. So I can figure it out pretty quick, and it's not going to take that long to hit 350,000. I forgot how many times I hit enter, but there's 1, 2, 3, 4, 5, 6. I only had to press it 7 more times, and it's already over 100. It's already over 350,000. So it's not like this is going to take years to double and get that many. I mean, that's going to happen within like 12 or 13 hours. It's pretty quick. Okay, so let's set it up and see what we've got. Okay, so initial amount, 100. What goes inside the parentheses for my, well, I got my initial amount, but what goes next to it for my number? 2. So my initial amount times 2 raised to the t divided by, what's the length of the time for the bacteria to double in this problem? It's every hour, so it's really just t divided by 1. Technically, you don't need to divide it by 1 here. So there's your formula. And they want to know when we're going to hit 350,000. So just be careful. There's 2 places where you could plug that in. Is 350,000 a time, or is 350,000 an amount? It's an amount. So you're going to put 350,000 on the left, and on the right. You can't do 100 times 2 and just say 200. You can't. It doesn't work that way because there's an exponent here. Order of operations, you got to raise 2 to the power first. Then you can multiply it after you do exponents. Okay, so we can put what's on the left in y1 and what's on the right in y2 to see where they cross. But I'm going to have to set my y max pretty high. It's going to have to be up over 350,000. So is there something I could divide both sides by? Yeah, we could divide by 100. That gets rid of that. So now I just have 2 to the t equals, you just cross off 2 zeros. I'm left with 3,500 on the left. Well, that's better than setting my window to 350,000. All right, so let's put it in and see what we get. And I don't remember exactly, but I estimated it. It was maybe like 11 or 12, maybe 13 hours. I'm not sure. It's however many times I hit times 2. All right, so 3,500 and 2 to the x. Okay, can I have negative bacteria? No. We're assuming that none of the bacteria dies, it just keeps doubling. So that's 0. How many times is it going to have to double? Well, I know 40 is way too many times. I think this doubled. I didn't hit enter 40 times. I think it happened definitely within 20. What should I set my y max to? I don't think 10 is going to quite cut it. Well, Naija, what do you think?
For the which one?
Y max.
The Y max. I'm not sure.
I would try like 4,000 maybe.
Yeah, because we put 3,500 in y1. So that's a horizontal line at 3,500. Unless you go at least to 3,500, you're not going to see anything for a horizontal. So Dominic said 4,000. I think that's perfect. There's your horizontal. And hopefully we went far enough that we see it. And you can see what happens to the amount of bacteria. All of a sudden, once it starts doubling, it takes off pretty quick. Okay, so Jackson, what do I do from there?
From there, you go and calculate,
Mhm.
and then you find the intersect.
Find the intersect. So, for 100 bacteria to hit 350,000, if it doubles every hour, it's going to take a little less than half a day. It's going to take about 11.8 hours. Right, so we've done 2 types of growth problems. One specifically about doubling, one that just had a random percentage. And the last one, we're going to do the opposite of growth. Specifically, we're going to look at the opposite of doubling. What's the opposite of something doubling? Yeah?
Divided by half of itself.
Dividing by... If you divide by half, I'm being picky, but that's technically doubling. Right, multiplying by half or dividing by 2. Okay, dividing something by 2 is the opposite of doubling. Well, something cutting itself in half each time has a name, and that's called half-life. A lot of times you might hear about half-life if you look up like something radioactive. I think we looked it up last week when I did it. If you look up uranium, the most common form of it that's radioactive, has a half-life of over 4 billion years. So what that means is if they're at a nuclear power plant and they make 2,000 pounds of nuclear waste, it's going to take over 4 billion years for half of that waste to decay into something that's safe. It's going to take another 4 billion years for half of what's left after that to decay into something that's safe. So that's the problem with some things that are radioactive. They take a very long time to decay until they're safe. But yeah, if you look it up, like uranium, I think it's like 4.5 or 4.6 billion years. And the formula is going to look very similar to doubling, except what do you think I'm going to have instead of a 2? I'm going to have a 1/2. Other than that, it's exactly the same. Right, so we'll finish up with a decay problem. in our problem, the half-life isn't going to be anywhere near billions of years. It's going to be 20 days. So we've got some substance, and every 20 days, you only have half of that substance left. So think about if you had 80 pounds of the substance, 20 days later, you have 40. 20 days after that, you have 20. Another 20 days, you have 10. It keeps cutting itself in half. Okay, so we're starting up with 5 grams. Okay, so Tyler, based on a half-life of 20 days and an initial amount of 5 grams, can you tell me the formula that describes the half-life here?
Like the initial amount of 5 using it, right?
So the initial amount is 5.
And then divide that by half, or half.
You said divide by a half?
Yeah, it's not 1 half next to it, right? Yeah. The initial amount is
Divided by a half or times a half?
times a half.
Times a half.
And then maybe like t by like 20 or something like that.
And then the exponent is t over 20. So the exponent has to be the number of half-lives that have gone by. So if it's 40 days, that's 2 half-lives. Okay, so there's our formula. So find an algebraic representation. Okay, we did that. All right, let's graph it. Now, this is a decay problem. What's the most amount of substance that we're starting with? How much? 5 grams. So we're never going to have more than 5. And if we keep taking half of it, what's it going to get closer and closer to as time goes on? 0. Will it ever be 0? Tom?
No.
No. That's the problem with something that's like nuclear. It never goes away. You can take half of it, and then half of it, and then half of it, and half of it. Eventually it becomes small enough that it's not harmful, but it's still there. Right? We just keep taking half of it each time. So let's not go below 0. And I'd say let's look at this for 80 days. If the half-life is 20, 80 days is how many half-life cycles? How many? 4. So that's half of a half of a half of a half. That's half, quarter, eighth, 16th. So we're going to have a lot less than 5 by the time we get all the way to 80 days. We don't need to go that far. But that's our window. Let's type in 5 times 0.5. If you want to do 1/2, you can. Maybe I should show you how to type it in as a fraction. Let's do it like that. I know the exponent's a little hard to see, but that's what it looks like. 5 times 1/2 to the x over 20. Okay, hit graph. So there's your substance decaying over time. Notice it's getting closer and closer to 0. It's never going to be gone. You're always going to have a little bit left. Okay, and they want to know, when are we going to have less than 1 gram left? So what would I do to find out when I have less than 1 gram? Okay. This is the 3rd time we've done it, so it's nothing we haven't already done today. How would we want to know on that graph where it hits 1 gram. I can't see it right now. So what am I going to do to make it easier to see where that graph hits 1? Well, we don't have anything to calc yet because we only have 1 curve on the screen. Right?
You have y equal 1.
Right. Remember when we did the population was like 100,000 and then it was equal to a formula? We had to put something in y1, something in y2. So we have to put a line at 1. Now we can calculate something because we have two things on the screen. What would you want to calculate?
The intercept.
Yeah, I want to calculate the intercept. So for 5 grams to decay to less than 1 gram is going to be anything from this point forward because it's going to keep decaying. So I would say anything from day 46.4 and on. So when will there be under 1 gram remaining? When I use for my letter T? T is greater than 46.44 days. It's just going to keep getting smaller and smaller and smaller as time goes on. And that's a decay time. All right, so let me double check. 47. So that's, I think that should be good. So it's 4 through 7, 19, 25, 31, and then 47 to 49, 57. Okay, we'll take a look at that tomorrow. What's that?
So do we need the 4 through 7?
4 through 6, yeah, that's the homework.